Good morning, students. In today's class, we'll discuss about the electrical conductivity or the conductivity of semiconductor. So before that, we need to again recap whatever we have completed in the last class. So we just started with the semiconductors, and semiconductors are the materials in which the electrical properties of the given material lies between conductors and the insulators. We just say that such materials are nothing but semiconductors. So the semiconductors are having various applications in the daily life and also in different aspects of engineering, as you know. So how this particular properties can be determined. So if I'm saying that the electrical conductivity of the semiconductors are lying between conductors and insulators, and that particular properties can be determined by the structure of the crystal, right? Since it is solid material, so we say that this particular intermediate properties can also be determined by the crystal structure bonding and the different characteristics. So since we are concising our talk to the semiconductors, which are pure semiconductor for some time. So silicon and germanium are the semiconductors which are said to be the intrinsic semiconductor, or we say that that is called the pure semiconductor. So when we go inside the silicon and germanium, you'll find that there are in the silicon element and germanium element, they will have the 4 valence electron, and the hybridization which is taking place inside this two semiconductors, intrinsic semiconductors, that are sp3 hybridization. And this particular crystal structure of the silicon and germanium comes to be under the diamond cubic crystal structure. Now, this is for your information, right? So, how the semiconductors are related to the crystals, what we have studied in the unit 1. Actually, semiconductors, as I said to you, have been classified in 2 important categories, that is intrinsic semiconductor and extrinsic semiconductor. So, extrinsic semiconductors are also known as impure semiconductors. So, as we go inside the intrinsic semiconductor, so the semiconductor which is it doesn't have any impurities, or just say that is pure, it will be a pure semiconductor. And how this semiconductor is related to the temperature means what is the effect of the to the semiconductor with respect to the temperature. We need to study this particular aspect. So what we are doing is that what is happening to this element when the temperature is 0 Kelvin. Now the question arises that why we are not going for Celsius, right? Since this particular semiconductor will have a different character at low temperature. So that is the reason that we are just concising our study to the Kelvin. So at 0 Kelvin, the same element will behave as an insulator, right? So if I increase the temperature beyond Kelvin, 0 Kelvin, then that particular same element will now act as an intrinsic semiconductor, or we just say that that is a pure semiconductor, right? Now, when we see the schematic diagram of the what you can say silicon, you can just find out how this bonding is formed. So let us consider, we just taken a 2-dimensional view of the silicon. You can just find that at the valence electron, see, you can just see a circle is there, and each circle of the silicon, you'll find that dotted region is having 4 electrons. So when these neighboring silicon atoms, when they are combined, so you can just see the structure, schematic structure of silicon is like this. And when we compare this any two silicon atom, you can just see that there is a bonding which is formed here. See, when I consider this silicon and this silicon, the bonding is formed in between these neighboring atoms, right? And when I consider this and this, the bonding is formed between these 2 electrons, between the 2 neighboring atoms, and so on. And this particular dotted line is nothing but it is a valence shell. So with this brief theory about the intrinsic semiconductor, now we'll actually move to our main topic. And until this, you have already studied, right, this in the lower classes. Now in engineering, what we are doing is that since in the last few class, a few classes in the same chapter 1, we studied about origin of energy bands in the solids. So we just have studied that what is actually the conduction band and how this conduction band is formed, and what is valence band and how valence band is formed, and what is the gap in between these two bands are said to be the energy band gap. So in the previous classes, we have just considered the isolated atom, in which we come to the conclusion that there exist the bands in the solids. And why we need to study these bands in solid? Why? Because we want to know that how the solids have been classified into conductors, insulators, and semiconductors. For that particular reason, we have known to this fact that the solids will behave as not only the conductors and also semiconductors and insulators. Now, with this a small schematic diagram, you can see on your screen that where actually valence band is situated and where is conduction band is situated, and what is the basic gap in between this valence band and the conduction band. As you can just see that this is valence band and this is the conduction band. So at 0 Kelvin, all the valence band is completely fixed. So now what is happening in the valence band? You'll find that there are numerous number of electrons at 0 Kelvin, right? Which is not shown in this particular schematic diagram. So as I increase the temperature to some K Kelvin, right? So what will happen? The electrons which are there residing in the valence band will move to the conduction band. And now the empty space of that particular electron, which is actually there in the valence band. So as the electrons have been moved from this valence band to the conduction band, you can just see that this empty space is represented with a circle, right? This is empty space, and what we call this empty space, which is left behind by the electron when it is moving from valence band to the conduction band at some K Kelvin. So now we just say that these empty spaces are nothing but holes which are positively charged. Right now, as the electrons are moving from the valence band to the conduction band, now this is the way how the electrons will move inside the conduction band, and this is the movement of these. Either it may be the holes or it may be the electrons. We just say that the kinetic energy of the whole is given by, in the case of valence band, is given by the is given by EV minus E. What is EV? EV is nothing but this is the highest value of the valence band, right? And this is the lowest value of the valence band, which is nothing but we just consider it as minus infinity. Clear, everybody? Now, when we go to the conduction band, the lowest value of the conduction band is said to be EC. So as we move to the highest level at this surface, we just say that is called infinity, right? So now the total energy is given by E. So we need to calculate what is the kinetic energy of the electron. So we just had E minus EC is considered to be the kinetic energy of the electron, right? Clear, everybody? So on the x-axis, we have just taken the distance between the two consecutive neighboring atoms, and at the y-axis, the electron energy, right? So now, as we move to the next one, so we just discussed in the last class the carrier concentration in the intrinsic semiconductor. So as you know that the electron, when it is given a suitable, comfortable amount of energy, it will move to the valence band to the conduction band, and hence the electron is very free in the conduction band, and simultaneously you find that the hole in the valence band is also free, and this particular phenomena of free hole and free electron are said to be hole pair generation. Now I will come to our actual what you can say topic, that is carrier concentration in the intrinsic semiconductor. So as you know that intrinsic carrier concentration is nothing but the number of charge carriers or the number of charge carrier which is present in the either bands. If it is in the case of conduction band, the number of charge carriers per unit volume is said to be the carrier concentration of that conduction band, and the number of charge carriers which are residing in the valence band per unit volume is said to be the carrier concentration of the are said to be the density of the holes which are residing in the valence band. So now with this we just calculate the density of electrons, and also we need to exactly calculate what is actually mathematical equation or relation of carrier concentration of intrinsic semiconductor. So in today's topic, we just have a very quick idea about what is actually carrier concentration of the intrinsic semiconductor. So since you don't know anything, now what we just start with our assumption, let us consider the Dn, the number of electrons which are available with the energy interval E and E plus D. As I said you that in the conduction band, you'll find that there are numerous number of electrons which are moving from one region to the another region inside the conduction band. So let us consider the energy E as at the at a particular level inside the conduction band, and E plus dE is the difference, which will be the energy of the electron as it moves from one region to the, or you can just say from bottom of the conduction band to the surface of the conduction band. Definitely there will be some amount of difference of energy in the with respect to the electrons which are residing in the conduction band. So how do we need to calculate the number of electrons? So first of all, we need to calculate what is the total number of electrons which are there inside the conduction band by using some simple mathematics. See, directly we don't know how many electrons are there. So what we are doing is that let us consider Dn as a small amount of electrons which are residing inside the conduction band is nothing but it is a product of the density of energy state, right? And the amount of probability of the holes or electrons which are electrons, right? Here f of E is nothing but the amount of electrons which are a probable electron. The probability function f of E is nothing but is a probability function which will give us the information regarding the occupancy of the electron. How much the electrons can be accommodated inside that particular bond is given by mathematically f of E. And this is the density of energy states in which how many energy levels are, what is the energy state of the given electrons, right? Which is given by the formula or the factor parameters n of E, dE. So now we just integrate this particular equation, n is equal to integration of, so definitely limits will be there. As you see, we have seen that we are just dealing with, first of all, electrons, right? Density of electrons in the conduction band. In order to calculate the actual carrier concentration of intrinsic semiconductor, we need to calculate both the density of the electrons in the conduction band, and also we need to calculate the density of holes in the valence band. So when we combine this density of electrons and density of holes, right, together, we'll get the carrier concentration. So n is equal to integration of EC to the top of the band, or we just say that is the infinity, right? Because we don't know regarding the upper limit of the conduction band. So we just consider that as infinity, and the lower limit is EC. So now Z of E, F of E into dE is equal to 1. So now where Z of E, dE is the nothing but density, either is equal to Z of E, dE is nothing but the density of energy states with the energy intervals E and E plus dE, and f of A is the probability of occupancy of the electron. So now, what is density of energy state? That is nothing but number of energy states which are residing per unit volume with the energy intervals of E and E plus D. Now, this is the formula, right? The density of energy state, mathematical equivalent or mathematical relation of the density of energy state, which has been already derived, right? We are not going in depth of that derivation of how the Z of E dE is nothing but this particular equation. So what we are doing here is that we just uh, considering that particular equal relation, right? So we just you should be by hearting this particular relation, right? So if you want to, we can have the discussion regarding how we got 4 pi h cube 2m whole to the power of 3 by 2 e into e to the power 1 by 2d, right? That particular discussion can be done, right, in the later part. So whenever you are having some doubt regarding this, right? So just for now, we just by heart this 4 pi h cube 2m whole to the power of 3 by 2 e to the power of 1 by 2 dE, right? So now Z of E dE is equal to 4 by h cube 2m e asterisk. Why we are going asterisk, right? Where m is the mass of the electron. Since the electron is free, so it will have some effective mass. And m suffix c asterisk indicates that it will have some effective mass. So 2m e asterisk whole to the power of 3 by 2 e to the power of 1 by 2 into d. Right now, when I say E is what actually it is starting from the bottom of the conduction band. That is the minimum value. That is the EC. So now, what is the kinetic energy of the electron? So we already know the kinetic energy of the electron. We can see this kinetic energy of the electron. See, kinetic energy of the electron is given by E minus EC. The E minus total energy is E, and the lowest energy is EC. So the kinetic energy of the electron in this case is given by E minus EC. So instead of E, I can write E minus EC. Right? Clear, everybody? So now, what is this probability of electron occupancy? So as I told you that f of E is nothing but it is the Fermi function, or we say that that is called the probability of the electrons which are occupying the conduction. Probability means approximately. So that approximation, mathematical approximation, is given by 1 by 1 plus exponential of E minus EF by KT. So for this particular aspect here is you need to again just remember this particular value, since it is a basic equation, basic relation of the electron occupancy is f of E is equal to 1 by 1 plus exponential of E minus EF by KT. So now you need to remember these two equations. What is Z of E and what is F of E for now, right? For all possible temperatures, we say that E minus EF is very much greater than when compared with the KT. So what will happen is that since E minus EF is very much greater than KT go to the down. So what will happen is that E minus EF by KT is very much greater than 1. So what we can say that in this particular factor, 1 is very, very small when compared with E minus EF by KT. Now, why I'm saying that 1 is very, very small? So since it is exponential, when you say the exponential, E to the power, it also resembles that exponential is nothing but E to the power of E minus EF by KT value is very much greater than 1. So this can be neglected. So I'm just neglecting this 1. So f of E is equal to 1 by exponential of E minus EF by KT. So when this exponential of E minus EF by KT, when it goes to numerator, so what will happen? F of E is equal to exponential of minus will come to the what we can say the starting point of this bracket. So E minus EF by KT, and now this particular value will be reduced to exponential of EF minus E. Minus will go inside. Minus into plus is minus. So minus into minus is plus. So EF minus E by KT, the exponential of EF minus E by KT. This is the basic simplified value of F of E for the occupancy of electron. Now I will actually go to our main value. N is equal to integration of EC to the exactly the upper value of this. That is infinity, or we say the top of the band. So Z of E into F of E is equal into V. So we just write instead of Z of E, whatever we have written, 4 pi h cube 2 m E asterisk whole to the power of 3 by 2 E minus EC whole to the power of 1 by 2. Now F of E value is nothing but exponential of EF minus E by KT. Just we are replacing whatever we have simplified in the previous slides. You can just see the previous slide. You can just pause the pause this slide, and then you can just see how I got this Z of E uh, for your reference, right? So this is the value what we got, exponential of EF minus E by K with TDE. So I'm just taking out this particular term. See, I already told you top of the band, it may be infinity. So we just written here infinity, right? So 4 pi h cube 2 me asterisk equal to the power of 3 by 2. So just take this part will parameter will go so from inside to the outside. So here integration of EC to infinity E minus EC equal to the power of 1 by 2 exponential of EF minus E by KT into D. Now this particular part, see, you already know that this again I'm just taking out this exponential of EF minus E by KT in outside this integration. So what will be remaining inside the integration? EC to infinity, lower and higher limit, E minus EC whole to the power of 1 by 2 exponential of EF minus E. See, you need to understand this. The e to the power of EF minus E by KT can also be written as exponential of EF by KT separately into exponential of minus E by KT. This you need to remember this, right? I think that this is a basic mathematical what you can say is the mathematical steps that this exponential of EF minus E by KT can individually written as exponential of EF by KT and exponential of minus E by KT, right? Now, how to solve this equation? Since it is inside the integration, we need to solve it. So what we are doing here is that we are just writing it at E minus, let us consider E minus EC is some X. So E is equal to EC plus X. When you just differentiate this, DE is equal to DX. This part will be 0. As you know, DE value is nothing but DX. Now, for now, definitely when you consider any factor inside the integration, the limits of this value will also change. So we just calculate the limit E minus EC whole to the power of, so the instead of here, instead of E, I am replacing the lower limit. So 0 minus EC is equal to X. So what will happen to the lower limit? X is equal to 0 as it is, right? Okay. And higher limit is infinity. So what we are doing, E is nothing but infinity. Instead of E, C replace E infinity minus EC is equal to 0. So what will happen? X value is what? Infinity. So the lower limit is 0 and the higher limit is infinity. Clear, everybody? So you need to replace the limit of lower and higher and in the place of this E. You have to remember this. In place of E, we need to change the limit. So what are the limits? Previous case, see the limit is EC here, right? So I'm just replacing that EC E at the whatever we have considered the equation E minus EC. So here, just replace it, you will get the value of X 0. And here definitely if you just if you add with something with infinity, or if you divide, if you subtract something with infinity, the value will be as it is infinity, you will get, right? So now E minus EC is nothing but x to the power of 1 by 2 exponential of E is what you know, EC plus x. So EC plus x, you can just see this factor E is nothing but EC plus x. So just replacing that, so you get this value as n is equal to 4 by h cube 2 me as equal to the power of 3 by 2 exponential of EF minus EF. See again what I'm doing, since it is a separate term, so exponential means this can also be written as exponential. This minus EC will come here. So exponential of EF minus EC by KT, taking outside x to the power of 1 by 2 exponential of minus of x by KT. Now this is equation number 3. So there is a, in mathematics, there is a relation that when the integration of 0 to infinity is there, and x to the power of n 1 by 2 and exponential of minus x, right? It should be dx here actually. So now that can be written as root pi by 2. So whatever the integration in this particular part, see, in the mathematics we are having the formula. If this is the relation, this can be replaced with root pi. See, this is replaced by root pi by 2. So now substituting in this equation 4 pi h cube 2 me as equal to the power of 3 by 2 exponential of EF minus EC by KT. So what will run root pi by 2? All right. So what will happen is that it will go inside pi. See, root pi by 2, root pi already it is there. So now this will go inside and 2 pi me as KT by h square 2 into, now this 4 and this 2 will get cancelled. That should be very much clear to you. So what we are doing here is that just multiplying it and keeping inside this see, this pi and root pi is nothing but pi to the power of 3 pi. It should be clear to you. This pi to the power of 1, pi to the power of 1 by 2. So this will come to pi to the power of 3 pi. So whatever the thing is remaining, this is the number of electrons which are present inside the conduction band or unit volume of the, or we say that there is a number of electrons which are present inside the conduction band. In the same case, right, what is the number of holes inside the what you can say, the valence band? The same way, only the replace part, what you will get for the valence band, the same aspect. See, instead of E, you will get MH asterisk whole to the power of 3. Now that part, so instead of C, E minus EC is there, here you will get EV minus. So that, right now, for that instant, we are not going right far about this particular equation. Now you can just see this is what we got z of e into, and the 1 minus f of e is nothing but the Hole's occupancy. F of e is what? Electron occupancy. So instead of that, we just replace and see bottom of the band E. So now this particular aspect, you can just see this, instead of E minus EC, what we are considering for the density of holes, EV minus E is equal to X, and we'll get in the same. Now this will be your equation for the number of holes, 2 into 2 pi mh. Instead of that, E was there in the previous case. Here mh asterisk kt by h square whole to the power of 3 pi exponential of E1 minus EF by kt. Now this is EV minus EF. There was E there in the previous case for electrons. It is EF minus EC. Here EV minus EF by kt. Everything is same. You can understand. See, the number of charge carriers for the valence band, the number of electrons for the conduction band, the number of the holes for the valence band, we just calculated. Now what we have to do is that how we'll get the carrier concentration. So in intrinsic semiconductor, you'll find that the number of electrons and the holes are same. So hence n is equal to p is equal to ni. It's called so So that is the reason that Ni square can be equal to Np. So Ni square, Ni is equal to root of Np. N is nothing but the density of electrons in the conduction band, and P just now we got the density of the holes in the valence band. So just replace that particular value, whatever we got for density of electrons, we are just replacing it, and you get this particular product. So when you see Me asterisk 3 by 2, Me asterisk 3 by 2, and also whole to the power of 1 by 2. So you'll get Me asterisk MH whole to the power of 3 by 4. This is same, right? Apart from that, 2 pi kt by h square. Here also 2 pi kt by h square. This is same. So when you just multiply it with the root, you'll get what? 2 into 2 pi kt by h square, 3 by 2. Me asterisk MH asterisk whole to the power of 3 by 2 exponential of EV minus EC by kT. So how I got EV minus EC here? So you can just EF minus EC plus EV minus EF. So plus EF minus EF will get cancelled. What is remaining? EV minus EC is remaining 2 by 2. So therefore, so we just got the value of Ni is 2 into 2 pi kt by h square whole to the power of 3 by 2. Me asterisk into mh asterisk whole to the power of 3 by 2. Now exponential of minus Eg by 2 kt. Now this is the value. And why I'm writing here Eg? Since you can just see the previous diagram, we have written the kinetic energy of the conduction band of the electron is nothing but Ec. So the kinetic energy of the holes in the valence band is Ev. So when I just the values Ev minus Ec will fetch me the gap which is between lying between the what you can say the valence band and the conduction band. See, that is the reason that we are writing it here as Eg. So Ev minus Ec is nothing but mathematically is nothing but E minus Eg. So minus Eg by 2 kT. So now with this, we just come to the exact what is actually the intrinsic carrier concentration. So we know Ni we have calculated. Ni is nothing but the carrier concentration of intrinsic semiconductor. Clear, everybody? So now, as we move to the what is actually Fermi level, mathematically, just now we can consider the schematic diagram. Here we are moving to the Fermi level in the intrinsic semiconductor. So the Fermi level in the intrinsic semiconductor, in intrinsic semiconductor, you know that N is equal to P. So we just whatever we got N value and P value, equate it, take the logarithm with some mathematical steps, you will get this. See, this we need to calculate this EF. So EF, what we are just written EF, right? Clear, everybody. So here, what will happen is that the effective mass of the holes and electron will be approximated to be equal, right? So when you just take this as a x-axis temperature, this is happening with respect to temperature. This should be very, very clear to you. So here, the total energy is electron, right? Electron energy is given. So you'll get EF is nothing but EV plus EC by 2. Means the Fermi energy is located. We want to locate, see, we have just written approximately dotted with dotted line. So we just want to locate where actually Fermi level, energy level is located mathematically. So we got the equation with very simple mathematical steps. EF is equal to EV plus EC by 2. Now this is the Fermi level of the energy. So what is actually the extrinsic semiconductor? So just now, whatever we have calculated, that is for intrinsic semiconductor. Now here we are just going for in extrinsic semiconductor. So extrinsic semiconductors are nothing but they are the semiconductors which has been classified in two different categories. That is N-type semiconductor, and also we just say that is called P-type semiconductor. Why we call this as extrinsic? Because of its impurity. They possess some impurity. So why we are adding some impurity? So we want to increase the electrical conductivity of this particular material. So now intrinsic semiconductor will have some electrical conductivity. So we want to increase that electrical conductivity value. So what we'll do is that we'll dope the impurity. We just yeah, I think that you studied about doping, right? Adding impurity to a pure semiconductor is nothing but it is called doping. Now, since the impurity is added to a intrinsic semiconductor, now the semiconductor is said to be extrinsic semiconductor, and these extrinsic semiconductor, depending upon the doping elements and valence electrons which are present inside the elements which are used to dope the pure semiconductor, so that depending upon them they have been classified into N-type and P-type. So when a see, they can do that. Pentavalent means what? 5 electrons are present in the valence. You already know that. Just now we seen the schematic diagram of silicon where the valence electrons are 4. here what we are doing is that since the silicon will have valence electron 4, apart from that, some impurity element, that is element we are just considering it as phosphorus. So if that phosphorus you can have the, why we are calling pentavalent? So phosphorus is having valence electron, is having valence electrons of the phosphorus is 5. So when I add that particular impurity to the pure semiconductor, then I will just say that is called the pentavalent element. So when any pentavalent element such as phosphorus, arsenic, or antimony are added to the intrinsic semiconductor, now the covalent band will be formed in between the 4 electrons of either silicon or germanium with respect to the place. Now the 5th electron is deeply bound to the parent atom, and even for lesser thermal energy, it releases, leaving the parent atom positively. Now this particular aspect you studied in your chemistry also. Now you can just see this silicon, silicon, silicon atom. So what we are doing, we are adding the phosphorus one. So you can just see there's a phosphorus. See, this is what silicon atom. How many electrons are there? 4 valence electrons. You can see 4, 1, 2, 3, 4. Phosphorus is having 5, right? So this is called dome. It will give its atom to the neighboring atom of silicon. So we just say that this particular semiconductor is exhibited this type of property as an n-type semiconductor. So we just say that is called n-type semiconductor. See here with schematic diagram, conduction band will be there, valence band. The donor level is given by like this, right? Now this you already know what is the value of each. Just now we calculated. So the carrier concentration of so we don't see for the syllabus you don't have carrier concentration, so we are not interested in this. So now we can just say, now we just move to the p-type semiconductors, right? So when a trivalent impurity such as we just see again, I'm taking a pure semiconductor, that is either it may be silicon or germanium. To this semiconductor I'm adding aluminum, gallium, or indium. This aluminum, gallium, and indium as an element whose valence electrons are having three valence electrons. This is added to the intrinsic semiconductor. So now these valence electrons is involved in the covalent bonding with the neighboring the silicon atoms, right? So we just say that this particular, if you add trivalent impurity, and we say that is called acceptor impurities, or we say that is called p-type impurities. You can just see here. Again, we have taken silicon and indium is there. So this indium atom is forming a band with the valence electrons of the silicon. So these are the covalent band. So this is this part we already studied in lower classes. Since you studied it, so we just had a very quick idea what is actually the intrinsic semiconductor, extrinsic semiconductor, and how these extrinsic semiconductors have been classified into p-type and n-type depending upon the impurity element and the valence electrons which are residing in this element, which has been inserted inside the pure semiconductor to make it extrinsic semiconductor, right? So I think that you got a very clear idea regarding what is actually the carrier concentration of the intrinsic semiconductor mathematically, what is the Fermi level mathematically, and also theoretically, whatever we have assumed, right? So now this particular point, see why we are all these things, the mathematical steps and so on. So mathematical calculations we are coming to. So we want to show that whatever the theory, what we consider, that theory can be verified mathematically, and with this particular fact, so we say that the charge carriers which are there in the semiconductors, there are two types of charge carriers. Theoretically, we say that the charge carriers in the semiconductors are nothing but both electrons and holes. So these two charge carriers are existed. So how that existence can be shown by means of some mathematical calculation. So just now we had the mathematical calculation regarding this extrinsic and the intrinsic semiconductor. Thank you, everyone. Thank you for your patience.